Meet Melvin, the friendly spider. Isn't he cute? It just so happens that Melvin is no ordinary spider. He's a mathematical spider. Okay, now you're probably rolling your eyes about now, but bear with me. We're going to use Melvin to introduce a mathematical curve called a parabola. Take another look at Melvin with some lines and curves drawn in. Notice the red curve connecting his knees. In mathematics, this red curve is called a parabola, and it represents the graph of a quadratic equation, y equals ax squared plus bx plus c. Parabolas have different characteristics. They look like a U or an upside-down U, and the bottom or top point of that U is called the vertex of the parabola. The vertical line through the vertex of a parabola is called the axis of symmetry, and the parabola is symmetric with respect to this line. There are two more characteristics of a parabola that we are interested in for this lesson, and those are the focus and the directrix of the parabola. We can use these characteristics to formally define a parabola. Let's get back to Melvin. As we said, Melvin is a mathematical spider, and another neat thing about him is that for each of his legs, the length of the leg from his head to his knee is equal to the length of the leg from the knee to the foot. Because of this, Melvin's head and the line where all his feet hit the ground are two very important characteristics of the parabola connecting his knees. To introduce these characteristics, let's look at the formal definition of a parabola. The formal definition of a parabola is the set of all points that are the same distance from a single point of the parabola, called the focus, and a line of the parabola, called the directrix. Now let's let Melvin illustrate this. We see that the parabola connecting his knees is such that the distance from Melvin's head to the parabola is the same as the distance from the parabola to the ground. Do you see how this relates to the formal definition of a parabola? If you're thinking that Melvin's head and the ground have some kind of relationship to the focus and directrix of the parabola, you're thinking correctly. Since each point on the parabola is the same distance from Melvin's head as it is to the ground, it must be the case that Melvin's head is the focus of the parabola and the ground is the directrix of the parabola. Pretty neat, huh? Let's take a look at an example. The parabola shown on screen has its focus and directrix labeled, as well as 2 points on the parabola. By the definition of a parabola, the distance between the focus and a point on the parabola should be the same as the distance between a point on the parabola and the directrix. Let's verify that this is the case. First, let's look at the point P1 equals 4, 2. All we need to do is verify that the distance from the focus F02 to the point P1, 4, 2, is the same as the distance from P1 to the directrix, y equals -2. We see that FP1 equals 4, and that the distance from P1 to the directrix is 4. Great! Just as the definition implies, the distances are the same. Let's do the same thing with the point P2 equals -8, 8, just to be sure. Again, we find the distance from the focus, f equals 0,2, to the point P2 equals -8, 8, and we find the distance from point P2 equals -8, 8 to the directrix y equals -2, and verify that these are the same. Awesome! Once again, we see that the distances are the same. We have that fp2 equals 10, and the distance from P2 to the directrix is 10. A parabola is a curve representing a quadratic equation y equals ax squared plus bx plus c. It has the shape of a U or an upside-down U, and the lowest or highest point of the parabola is called the vertex. The vertical line through the vertex is called the axis of symmetry of the parabola, and the parabola is symmetric with respect to this line. The formal definition of a parabola is the set of all points that are the same distance from a single point of the parabola, called the focus, and a line of the parabola, called the directrix. Wow, it's really neat to look at parabolas in this way, and it's great that we had Melvin, the mathematical spider, to help us along.
Remember the last time you played with blocks? Great fun! With lettered blocks, you can build words. It's amazing so much variety exists with only 26 letters. Also, the shapes of letters themselves are inspirational. For example, a parabola is shaped like the letter U. In this lesson, learn to build various equations for the parabola, given only the information contained in the focus and the directrix. Now those are words you probably did not see with your blocks. Start by drawing a line on a graph. In this example, the line goes through y equals -3 and is parallel to the x-axis. This line is called the directrix. Locate a point. In this example, the point is at 3, 1. This point is called the focus. The idea is to use only this information to plot a parabola and to find equations that define the parabola. The parabola corresponding to this directrix and focus looks like this. The distance from the focus to a point on the parabola curve is the same as the shortest distance from this point on the parabola curve to the directrix line. So the points on the parabola curve are equidistant or equal distance to the focus and to the directrix. Finding all the equidistant points is one way to plot the parabola. The blue lines on this image show the equal lengths. The turning point on the parabola is the vertex. On this example, the vertex is at 3, -1, which can be observed to be halfway between the focus and the directrix. Lots of words to build with our blocks. Instead of building words, this is building equations. Say the focus is here. The point on the line is xy. The location on the directrix will be at x alpha. Let's keep things general on purpose. In addition to the variables x and y, the equations will have your three numbers x sub 0, y sub 0, and alpha. The parabola equation in standard form for finding the length between 2 points is the square root of the sum of the squared differences in each coordinate. For this case, the length of the line segment between the focus at x sub 0, y sub 0, and the point on the curve xy is the square root of x sub 0 minus x squared plus y sub 0 minus y squared. The length of the line segment between the point on the curve xy and the point on the directrix x alpha is the square root of x minus x squared plus y minus alpha squared. The lengths are equal, so you can equate the two square roots. Then square both sides, expand, and isolate the y on the left-hand side of the equation. The right-hand side depends on x sub 0, y sub 0, and alpha. This equation has the same form as y equals ax squared plus bx plus c. This is the standard form equation for the parabola. Do you see how to find a, b, and c? The example parabola in standard form is y equals 0.125x squared minus 0.75x plus 0.125. Sometimes you're asked to find where the parabola intercepts the x-axis. To get an equation with this intercept information already in it, use the standard form equation with a, b, and c. Then factor out the a to get y equals a times x squared plus b times x over a plus c over a. Then use the quadratic equation to find the two roots p and q. The equation looks like y equals a times x minus p times x minus q. Now you have an equation which directly gives you the intercept information. The p and q are the x-intercepts. These are the places where the parabola curve crosses the x-axis. The example parabola equation in intercept form is y equals 0.125 times x minus 5.83 times x minus 0.172. Sometimes you'll want to know where the parabola has its vertex. To get an equation having this vertex information in it already, take the standard form equation and complete the square. The result is y equals a times x minus h squared plus k. You now have an equation in terms of the vertex. The h and k are the x and y coordinates of the vertex. This is the parabolic equation in vertex form. From our example, the location of the vertex is at 3, -1, which tells us h equals 3 and k equals -1. Thus, the parabolic equation in vertex form for this example is y equals 0.125 times x minus 3 squared minus 1. What happens if there are no x-intercepts? How could this happen? The parabola's curve might not cross the x-axis. When trying to compute the p and q values of the intercept form, you'll be attempting to take the square root of a negative number. This tells us no x-axis intercepts exist. If the parabola is concave downward, then A will be negative. If the parabola is sideways with its opening to the right or left, obtain the expressions by interchanging x and y. Building on our knowledge of the parabola is very much like building with blocks. The possibilities are vast. The directrix and the focus provide enough information to write an equation for a parabola. Any point on the parabola is equidistant to the focus and the directrix. Equating these distances leads to the parabola equation in standard form. There are other convenient forms for the standard equation depending on what information you need. For example, solving for the roots of the standard equation gives the parabola equation in intercept form. Completing the square in the standard equation gives us the parabola equation in vertex form.